Hi, my name is Abbie Martinez, and this is my lab report number 5 on the following Slinky. Introduction. So the purpose of this lab is to predict and analyze the motion of a Slinky falling from rest by comparing the observed model to a computational model. In particular, we want to determine whether the computational model for the Slinky stays stationary like in the observed model. Fundamental physics principles. There are two main categories of fundamental physics principles in this lab. First, Newton's second law, and second, the sum of forces acting on the Slinky. From Newton's second law, we obtain the velocity update equation and the position update equation, where V final and V initial plus F net over M delta T, and RF equals R initial plus V average delta T are used later in the code. F net consists of F grav, F drag, and F tension, aka the force of the Slinky. F grav equals negative mg and F drag equals negative bv squared in the upward y direction. Brief preview of main results. Both models indicated that the bottom of the spring remained stationary until approximately 5.8 seconds. When the top of the Slinky meets the bottom of the Slinky, both models indicated that the bottom of the Slinky steadily falls in the negative y direction. Models with descriptions. So here are the initial conditions set. The mass of the Slinky on line 29 is approximately 0.5 kilograms, and the position and velocity vectors on lines 31 and 32 come from the initial tracker data. The Slinky's initial position is 0, 4.1 times 10 to the negative third, negative 2.5 times 10 to the negative fifth meters. The Slinky starts at rest, so its initial velocity vector is 0, 0, 0. The proportionality constant was estimated, and g equals the gravitational constant on Earth, 9.8 meters per second squared. In this lab, the plus y axis points upward. So the Slinky's position was updated using two loops. The first while loop on the left is for when the top of the Slinky has not yet made contact with the bottom of the Slinky. The second while loop on the right is for when the top of the Slinky meets the bottom, up until hitting the ground. These time intervals are shown on lines 46 and 70. The content inside the while loops is the same for both, with the exception of how F net was calculated in each part. In lines 49 and 50, W and FT are equal and opposite in signs, illustrating how the bottom is not moving before 5.8 seconds. In lines 74 and 75, W remains the same, but now there is a drag force accounted for. Observed model. The Slinky was dropped from rest and the positive y direction pointed upward. We used point mass to track the bottom of the Slinky in this section and began tracking when the Slinky was released. The bottom of the Slinky started at the origin with the blue shirt pocket used for the calibration stick. On average, this was 0.102 meters wide. The system was the Slinky, and the surroundings included the air and the ground. Discussion and results. Main results. Both models indicated that the bottom of the spring is stationary until approximately 5.8 seconds. This is shown on both of the graphs, boxed in orange. When the top of the Slinky meets the bottom of the Slinky, both models indicated that the Slinky was steadily falling. However, glow-scope model on the bottom indicated a constant decrease in y position, while the observed model had more deviations and is less constant. This could be the result of drag force due to air resistance. Possible sources of error. When tracking the bottom of the Slinky in Tracker, the Slinky blurred between frames, making it difficult to track its exact position. Although both computational and observed models account for the drag force, due to air resistance, the observed model may not have experienced a constant drag force like the simulated in GlowScript code. Conclusion. What if we instead track the top of the Slinky? From release, the top of the Slinky steadily falls over time. Its velocity does not change when the top of the Slinky meets the bottom. This graph is shown here. This was similar to when the top of the Slinky met the bottom of the Slinky in the previous graph. And what if we instead track the Slinky's center of mass? The Slinky's center of mass is located at the midpoint between the top and bottom of the Slinky. This is seen on the rightmost image taken in Tracker, where the green is the center of mass and the bottom is the red, and the top of the Slinky is in cyan. The graph shown here follows the same steady decrease in y position over time as the previous graph. Thank you.